This is EE 380, winter 2022. And the speaker today is David Henkel-Wallace. And David is a longstanding Silicon Valley entrepreneur. And he is dead set to make the world safer by producing more CO2.
That's right.
In any case, the chair is yours, and we'll interrupt from questions perhaps over time.
Hi, I'm David Henkel-Wallace. What I'm going to talk to today is about climate restoration, that is, repairing the climate to make it more commodious to human life, and why we should be doing that. I'm going to talk about some projects in that regard, and specifically about my work and my team I'm working with's work on removing methane, which is one of the worst greenhouse gases, even worse than CO2, and trying to cut the temperature by half a degree. So climate restoration is an unusual term to most people. I talk to a lot of people about it who don't realize that it's even possible to fix things. Because mostly when you read the news, people talk about privation, right? You must eliminate emissions. And I think that's a good thing, but that seems to be pretty much how people think you can improve the climate. Somehow you're going to generate less CO2, emit less CO2. Abatement means instead of reducing emissions by not driving your car as much, but it means cutting off emission sources like oil rigs and things like that. And then the other thing which is conflated with that is we should switch to cleaner energy sources. And cleaner itself it's like the food plate from the Department of Agriculture. It's cleaner by a definition that's not normally used by normal human beings. For example, emitting methane is considered cleaner than burning coal. Over the past 2 or 3 years, the federal government in the US has started to recognize the idea that you might adapt to the climate, that is, build more seawalls, rebuild houses that get destroyed right in the place where they were destroyed, and in general, not do anything about the climate problem. But what I'm talking about today is, why aren't we cleaning up the mess in the first place? That's certainly what we would do if we had a big party in our house and the place were a mess. We wouldn't just decide to buy fewer Cheetos. We might say, hey, maybe I'll switch to something different. So that, and we would vacuum up the house. So we're right. I just want to tell you a little bit more. We're on an absurd path right now. Okay. The UN's position is that is to reduce the rate at which we cause damage. So basically, they're actually just decreasing the second derivative of the problem. I have a friend who calls this a suicide pact. And it really is, because all we're doing is we're literally kicking the problem down the road, but with no plans to actually even address it. Okay. And so I have this graph here, and it shows that I think people don't realize that we're going to increase the amount of CO2 by over 50% if the UN is successful, which to date, of course, they have not been. Our goal, if you look at this graph, is to take that green, follow the path of the green line, and bring the level of CO2 down below the level or around where it was in 1775, as I'll tell you. So the UN plan is to tolerate CO2 levels up at 450 parts per million. And the historic levels through human existence have been about 280, right? So the UN is basically willing to tolerate a temperature and CO2 level higher than humans have ever survived before. I have some more graphs about that. So our goal is to build a planet habitable to humans, right? And that's different from saying we're going to go back to exactly the way it was. I mean, this is hysteresis loops here, right? It's too late with already, mass extinctions and changes to the environment. We're not going to go back where we were, but we can go back to a place that is good to humans. We can bring the climate to a place that's good for humans, because after all, the planet doesn't care anyway. The whole purpose of this project is to terraform the Earth, and which is what we've been doing for the past few thousand years to make it comfortable for human beings. Well, I'll keep going anyway. Sorry, you can't see my graph. I have a graph. It's a pretty scary looking graph because this one shows carbon dioxide concentrations over the Holocene. And you'll see from over the last 100,000 years, the curve is basically flat, right? A little bit of noise, the curve is basically flat. And in 1775, suddenly the curve becomes almost vertical. So we're not going to go back to the status quo ante. But it turns out people don't really want to. Okay, people have adapted the climate. They've destroyed the forests because they've turned them into economic value, removed the dangerous animals, and we now have a curated environment. And for the foreseeable future, certainly my lifetime, we will continue to have a curated environment. As I said, there's too many hysteresis loops, and you just can't go back. Once you cut a forest down for firewood, it doesn't grow back up the same way because you've destroyed all of the undergrowth. Once you've done that, you've killed off a lot of the animals. They don't come back. But there's also scarier, more short-term problems that we're worried about. I think in the news recently, there have been some discussion about the melting of the Russian tundra, and frozen in that tundra is decomposing matter from the last ice age, and as it warms up, that's causing bursts of methane to be released into the atmosphere. But what I haven't seen in the popular press is the fact that also there was partially decomposed material that, as the heat as it's defrosted, has now started decomposing at an accelerating rate, just emitting methane at its on its own, not fossilized methane. And that methane, in 2020, methane levels rose twice as high as had been previously recorded. Okay, and nobody knows why. So the current theory is the melting of the tundra, and that tundra is on fire actually as we speak, and the Russian firemen are having trouble putting it out. Okay, so our target is to get the climate back. Since you can't see my graphs, our target is to get the climate back to something commodious to humans, to 1775 levels within the next 3 decades. Okay, by 2050, and we think it's possible. The reason I mentioned 1775, by the way, because of our audience here, is that's the year James Watt got his patent and set us off on this deadly path. Okay, so I've been a little cynical about the UN, and I don't mean to be, because they're actually reacting to what people want, which is they want to do as little as possible. They're busy. People are busy changing the environment all the time by driving their car to a mile to the grocery store to pick up one loaf of bread. There's a complex bit of geoengineering going on there, and nobody's going to stop that. Humans are going to human. So, what we need is to have. I think what people do, interestingly, react well to is private sector efforts to work on the environment. They're very excited if there's a direct air capture CO2 machine, because it feels like someone else is doing the work and I don't have to do the work. And we've adopted that strategy. And there are other people that I'm going to talk about who have adopted that approach, which is to find ways to profitably, or at least outside government and NGO activity processes to work on climate repair. Okay, there are already frameworks that you can fit in, from environmental studies, specially designed experimental regimes like the London Protocol, carbon certification trading, and the usual subsidies and tax efforts. And these transitional tools are still used at negligible levels, but they have caused a revolution in energy generation. And we and some others are surfing that same process to work on to actually start implementing climate restoration. Okay, so there's a psychological factor that we're finding people are responsive to, because all of us are busy changing the climate. We're just busy. We have the sign backwards, and so our group at Blue Dot Change, some other groups that I'm going to talk about, are making it easy for people to support working in the opposite direction. Okay, now I have a bias to techniques. Okay, so my bias is that we should use techniques that use mechanisms that already exist. That is to say, to accelerate natural processes for climate restoration. Now, if you could see my screen, and I'll try one more time. Okay, well, there is a nice graph showing that over the last million years, we've had 10 ice ages. So there's a pretty good, well-known technique, which we are not going to do, which is to detonate a ton of volcanoes, causing an ice age. And fortunately, nobody knows how to do this. But one of the interesting things, when you detonate a ton of volcanoes, you get an interesting cycle of process. First of all, you get a lot of shade because a ton of particulate matter goes into the upper atmosphere and sticks around for a year or two. But what's interesting about that material is it's full of iron, among sulfur dioxide, NOx's, all sorts of stuff, and that iron eventually washes out into the ocean and generates it fertilizes the ocean and causes a lot of algae to be born. And that algae in the short term is great because it chews up CO2, breathes out oxygen, and changes the temperature. Dies and sinks to the bottom of the ocean. The bad news about that is that as you heat up the ocean, as we do, as we're doing right now, then you change the density of the ocean, and a lot of that methane that was generated at the bottom of the ocean through the rotting of this algae suddenly starts to appear. And again, up in the Arctic, you can actually see bubbling regions of the ocean. But it gives you an idea of a direction you can go. So one of the reasons that I'm a fan of these natural processes is that these processes are powered through ultraviolet, and ultraviolet is provided for free. If you look at these direct air capture machines that people are trying to build, they need a large amount of power. And I don't have a graph of the calculation, but I actually don't believe it's thermodynamically viable to actually take teratons of CO2 out of the atmosphere with the energy capabilities we have today. On the other hand, we've got this great fusion reactor 93 million miles away that's sending tons of UV our way, and that UV is already used to sequester, to oxidize methane, to break down CO2, or sequester CO2 through vegetable processes, and it's free. It's already there. So I'm a fan of processes like that. The UV is used to sequester in biocarbon, and like through processes like I talked about, either kelp that the CCRC is experimenting with, or some of the processes that be done on algae, also used to break down methane in the process that I'll be talking about later in this talk. You can also look at human processes, at mineralization processes that are performed as a side effect of doing other human action. 90% of the CO2 that's been captured until now has been captured in biological systems and making limestone, which is basically the dead shells of sea creatures, with the phytoplankton. And so limestone can be, limestone's being produced already by some companies in the UK and a company here in Los Gatos, who are generating limestone and selling it for building materials. The guys in the UK have a process that actually also excretes fresh water. On the experiments that have been done on building algae, they've actually been using the algae to fertilize or to feed fish farms. So part of it sinks to the bottom of the sea, and part of it, of course, turns into fish, which people eat, and then they breathe the CO2 out. But it's still a net positive. So the whole point is to get the temperature back to normal. Okay, if we could use these processes, which is our first project, to get 60 gigatons of CO2 out of the atmosphere a year, we could get the climate down by the end of the century, the CO2 levels by the end of the century down to 1775 levels. Okay. Now, we have to talk about the deadly word, geoengineering. I know there's at least one person on this call who's a big fan of those processes, but every time it comes up, we get opposition. And the opposition is very interesting because basically anything that looks technical frightens people. And that's one of the nice things about these natural processes. Of course, they are engineered processes. I'll show you what we're doing for methane, but we are doing something deliberate to accelerate a natural process. But it's interesting to me that they're planting a green wall in Africa. They're trying to stop the Sahara Desert by building a 4,000-mile wall of trees. And it's incomplete, but it's already changing drought and monsoon patterns in Africa. It's clearly the geoengineering project, but since it's planting trees, it doesn't get people frightened. So although I feel from a thermodynamic reason that we should be using biological processes to restore the climate, it turns out to be less frightening to quite a few people if it has the word natural attached to it. Okay. The other thing about the processes I'm talking about, which should be familiar to a lot of the EE 380 viewers, is that these are processes that can start small and can be scaled linearly. Right? You can stamp them out by just applying money and effort. Not unlike starting out with one microprocessor and building a large machine out of a lot of them. These processes are easier, I found are easier for the lay public to understand than to build one big machine or put an umbrella out in orbit. Things like that really frighten people. But because they're just one thing, and I think these are the kinds of things that they see in the movies. So let me talk a bit about what we're doing when we're starting with methane. So the question is, why start with methane? Okay, there's only about 600 megatons of methane in the atmosphere at the moment. There's almost 2,000 parts per billion, 2 parts per million. And here I was talking about CO2, where it would have 300 parts per million. It would be ideal. And the reason for that is that methane is about 50 times as forcing greenhouse gas as CO2 is. Okay, so just that 2 parts per million of methane in the atmosphere has raised the temperature of the Earth by 0.5 degree. So if we can remove all the human-generated methane or more, then we can buy ourselves time, another 20 years, to continue working on some of the other problems that need to be solved. So that's why we are starting with methane. It's a smaller, more tractable problem due to an interesting chemical reaction, set of chemical reactions that I'll talk about. And it buys us time. It's of a tractable size that will buy us time to do more of the work that needs to be done. Now, methane is an interesting chemical because it is given off through biological processes, like CO2 is, but they're diffuse processes too, right? So I have this chart on the right. If anyone really wants to look at it, it's a bit of an eye chart there. I have a slide with just that picture on it. But what this shows is that humans generate about a third of the methane emissions. Actually, in 2021, it looks like it might have been a half. And it turns out that oil refining is not a lot of it. A lot of it's agriculture. Cows burping, not farting like everyone says, but burping. But it's also coming, the bulk of the natural methane is just coming from swamps. And no one's going to be able to fit a catalytic converter to a swamp, right? So regardless of any amount of human efforts to curb methane production, paddy fields, natural swamps, etc., they are just generating tons of methane each year, hundreds of tons of methane each year. Now, methane itself lasts about a dozen years in the environment and breaks down naturally into CO2 and H2O, and either through hydroxyl radicals or chlorine ions, which we're going to use the chlorine ion path. So the problem is, of course, because humans are pumping it out at a much greater rate than naturally occurring, methane, which is IR opaque and happily protects us under normal conditions, is actually now cooking us. So this is the problem we're trying to get through. Because of time, I'm going to skip forward a little. On the bottom of this, I talk about the fossilized methane. Okay, but here's the problem. Again, since 1775, that sort of time when we lost our ecological innocence and started mining the past, methane levels have almost doubled. In fact, they're now very close to doubles. Even the same time when CO2, of which there's a lot more, has only gone up 50%. And so the most potent greenhouse gas that's produced in volume is also the one that has been growing the fastest. Now, don't forget, when we switch, this is what I'm talking about earlier when I talked about switching to a clean fuel, natural gas, which is basically just methane, is considered by the UN and by the EPA, et cetera, to be a clean alternative. And it's true, it generates less soot. But what they never talk about is the soot and sulfur dioxide that's been put out by our old dirty technology has actually been cooling the earth by reflecting sunlight. As we've been cleaning that up, we've actually been heating the earth up faster by using a much more dangerous fuel. Since I don't anticipate that people are just going to throw away their natural gas investments tomorrow, they're going to wait for them to be completely amortized. We need to take action in the open atmosphere itself. And we're going to do that in the ocean. If you look at the methane, you can tell that the northern hemisphere has a hell of a lot more than the southern hemisphere. Why? That's because there's lots of people. But the earth mixes, and you see that the northern hemisphere is all about the same color, and the southern hemisphere is roughly all about the same color. And the nice thing about oceans is they don't have topographic features. The atmosphere mixes very well. So that's where we're gonna do our work. So what we do is we harness the natural process of methane oxidation that occurs in the troposphere, in the oceanic troposphere, that is the part that we breathe when we're sailing on the ocean. And what happens, what's interesting is about 15 years ago, some scientists in Europe, in Germany, started investigating the behavior of surface chemistry in the ocean, and they noticed that the salt spray in salt pans or just in the waves, of course, anybody who's been in the ocean knows it's full of chlorine. That salt spray actually degrades about 15% of the atmospheric methane. Now, it's catalyzed by the present naturally occurring NOx's and other pollutants. But what's very interesting about this is a French guy who figured this out, is that when the winds pick up the dust from the Sahara, the Mojave, the Sahara, and especially the Great Sandy Desert, they blow a teraton of iron across the ocean, some of which falls into the ocean to fertilize it. And of course, most of that dust from the Sahara feeds the Amazon. The iron in that feeds the Amazon. But what's interesting is that those iron salts in the atmosphere have a catalytic effect on accelerating the breakdown of methane. So our process is to spray iron chloride into the atmosphere over the ocean to accelerate the amount of that catalyst that's in the environment. It's going to have its own chlorine as well, and accelerate this natural process. So the nice thing about ships, we're actually going to spray it into their smokestack, into the exhaust plume, because that's got a lot. That's even with all the scrubbers, that's rich in NOx's and easy to track as it travels around. And one of my colleagues did a calculation. He said the entire atmosphere passes through a ship's exhaust every 6 months. It's pretty nice, pretty good to understand how much of the atmosphere you can get just by blowing this stuff in the out over the ocean. Of course, this is research, right? This has been validated in smog chambers in Bayreuth and in Copenhagen. But part of our job is to scale this up from bench top to the atmosphere, and that's the process that we're engaged in today. Now, how do we get it out of the ocean? It turns out that there are these ships that are driving around all the time. If you go back to that chart here, well, you can't see my finger, but you can see that ocean. You can see China on the left. That ocean to North America to the left. The transatlantic passage, and then on the right, the Chinese passage around to Long Beach. That whole region is hot. It's got a lot of UV. It's got a lot of methane in it, and it's all open water. So we're going to be doing this in the pelagic ocean, in the international waters. There's no topographic features. You get very good mixing, and it's easy to look at with a satellite. Okay, so it's interesting to look at this catalyst when we go back to this geoengineering question. If the catalyst that's available everywhere, it's decided, they make it in steel plants, it's used for water treatment, it's available in bulk. It's not like we're developing some exotic chemical. Those of you who make circuit boards, those of us who make circuit boards in the bathtub use it as well. It lasts about 10 days, mainly because it rains every 10 days or so out in that part of the ocean. It's going to wash out. So it's a continuous operation system, but you can turn it up and you can turn it down depending on how good a job you're doing, or of course, what kind of environmental issues you want to worry about. What's interesting is you don't need to do a lot of this. A few thousand ships is enough to get all of the anthropogenic methane, to address all the anthropogenic methane. And now, of course, that's modeling based on our model of scale up, but it's within, it's $1 billion, so it's within, we're within a factor of 2 or 3. We think of what it's going to be, and that's a pretty small number in the scale of things. Certainly a hell of a lot less than the government the government has decided to spend on building seawalls and rebuilding people's destroyed houses. Nice thing is, once you've got this deployed, you can just tune the system, right? Methane levels rise, you can switch on a few more ships. If we get a a huge methane burst from the Arctic that might destroy our agriculture for 10 years, turn on a lot of ships. It's easy. We've been talking with the ship owners, and it's surprising just over the past 2 or 3 years how much pressure they're coming into to do something about the climate. They're actually, you're sending your iPhones over from China to the US causes about 10% of carbon emissions, global carbon emissions. So they're pretty interested in being able to help. I think I probably talked about why ships, the pollute. This is a picture of the North Atlantic, actually, and just from a satellite, you can actually track. You can track the ships, even if they even if they switch off their transponder, you can actually track the ships when the atmospheric conditions are right, which is most of the time. So I think I've discussed everything on this slide, except we're in the process scale up. We're not in deployment scale up. We're in process scale up. Our plan is to start deploying late next year, or because things always take longer than you think, maybe the beginning of 2024. But we expect to have enough ships to get all the anthropogenic methane within 2 years. 2 years of beginning deployment. So we're doing pretty well on time, actually. So we're a startup company. We are an international company. These days, everybody's remote. I've got people in Europe, the US, Australia, working on this project. But I'm hiring specifically in the Bay Area to do the engineering. I'm looking for some chemies, some mechanical engineers, and some double-E's for the control systems management. Okay, what I am going to do is go to the front page where I put my email address. And the reason is I obviously went extremely high level. There's a lot of detail that any nerd would want to know. So I'm happy to answer questions after the fact as well. If someone wants to do a deep dive on, the photochemistry or whatever.